in the context of chapter 5 and what we're going for with this eigen stuff is our best case scenario. This is our favorite thing to happen. A is an n by n matrix with n linearly independent eigenvectors. We can kind of make an eigenbasis for Rn. That we can make a basis for Rn that's just all eigenvectors of the matrix A. When this happens, the matrix A is diagonalizable. What that means is that A is similar to a diagonal matrix. What that means is that there's a diagonal matrix D and an invertible matrix P such that A is equal to P times D times P inverse. The example that we had previously, the matrix B, was diagonalizable because B had 3 linearly independent eigenvectors. So the matrix D is diagonal, means it only has, the only non-zero entries will be on the main diagonal. And the matrix P has to be invertible. And to make this happen, we need n linearly independent eigenvectors. So that will leave us to we can just guess how we're going to make the matrix D and how we're going to make the matrix P. So this opens the question, where do the entries in D come from? And that raises the question, where do we get the columns of P? And I asked it in a very leading way. So, as you start working on the homework from chapter 5, it gets into 5.3, diagonalizing a matrix. This is what you're going to have to figure out. Where do you get the entries in D? Where do you get the columns of P? Remember, this is only possible if an n by n matrix has n linearly independent eigenvectors. That should tell you something about this invertible matrix. All right, let's pause the video here and then talk about some technical things that need to happen. Incidentally, this is the question. These are the questions that I'm not going to be answering today. So we'll have to find that out, or stay tuned until Wednesday.